I know.
I'll just wait.
Good.
That's why anybody wants to know.
So
What's he walking around with?
if he's not really trying,
Yeah.
144, 144, and he's waiting, 140.
Oh, yeah.
It's and Bob
I
Porter
mean, when
and
the season's
Oh, that's right, yeah.
really down
So I did. We already have
43
one.
Yeah, so, how does he want to rock this for 6 months or something?
Yeah, you don't lose it.
Yeah, exactly. But I was walking around like that.
Oh, it's
So we know that, Madonna might be able to make this really nice for her. I don't know, I think the person that I don't know keeps
Right, when I was out of shape, I'm sick, when I tuck away, when you get to college, like, your immune system needs to be strong so you don't catch up the nasty stuff on the mat. And then when you're cutting, like, it just kills your immune system. It makes you so susceptible to all the stuff going around.
Yeah, that's like he's on training party.
Tons of guys have like up over their dosing and everything. Yeah, so
Yeah.
you gotta account for that when you cut weight. So that was how we ended the season last year. This
Yeah,
year,
Dr.
you know, the strength of summer.
Do you guys need any donuts? I'll have some refreshments.
Better to, yeah, I really trained last year.
Please, take some donuts and coffee.
Now we see the weight class. So this tournament,
I think we do,
it depends on who's, going heavy and hot at the end of the season and all those different things.
I just said, well, take these.
For guys that are currently ranked in the
You don't need them, I will.
you know, right around these let's leave. Two and four and still be the eighth best wrestler.
No, that's a great opportunity. I always told myself when I hit ranked guys in the country or the state, it's expected for you to lose, and you can only do better.
Yeah,
You know what I'm saying?
yeah.
So let it fly.
I might have some, thank you. But he should be running forward with these guys.
Yeah.
See how it goes.
But another thing, don't worry too much about that.
Yeah, I
That's
know.
one thing people struggle with a lot. A lot of wrestling moms are always like, oh, this guy's ranked this, and don't ever worry about that.
I just share that with him. Now,
Yeah.
what he was on his own, I can't control.
Yeah.
I've never.
Especially early in year 2, you see these rankings, and at the end of the season, you're like, oh my god, remember this guy was getting big in place. So, yeah, it's all.
Yeah, there's this app now.
So like I should just grab a fresh batch or
I think they
something?
glean from track wrestling. It's
Just
called
2
Rank
weeks.
Wrestling.
Rank wrestler, yeah.
And it's like $25 for a year subscription.
Yeah.
And
About enough.
so I know these people who have it, and I'm like, it's tempting,
But
but
it's so tempting. My father never shut up about it. He was like the wrestling ranking high school connoisseur in New Jersey. If anything changed, everybody, that's my dad. And I know you're Ryan plays that. I'm not like, no.
What's that just for the other guy?
Yeah, it is very tempting. Yeah.
I mean, that's not our fault.
That's good though. So you want to go on?
I have stepson.
Okay,
I
cool.
just, this is up to his mom.
Yeah, and we can start.
Yeah, so I'm.
No?
Didn't see anybody else give me the interest of time?
Sure. Yeah, we can go ahead and get started.
Start right now?
Yeah, no, thank you for this.
Would you want
There's some coffee
something?
I might take you up on that. Let me just-
Yeah.
If you guys don't need it, I will after the meeting, so.
Perfect.
Right in, yes, sir.
Come on in. I'm Brian.
Nice to meet you.
Ryan Horn.
Yep. Brian and Bob. Nice to see you.
Nice to meet you.
All right, cool.
Nice to meet you, Fran, the library. Good to meet you, Fran.
Thanks.
Yeah, feel free to have a seat anywhere. There's coffee and donuts in the back. If you'd like some.
So you gotta get settled in.
Here, I would like to hand you our rubric and.
He's gonna try to make it. Okay.
In these rubrics that they've handed out, it's just a single point score per page. Some people try to divide it amongst the elements, but it's a single point score per page, and we use that to accumulate the grade for the student for this particular course. So your feedback is really helpful, and we're grateful that you're here.
Okay, that's all. I think we, in the interest of time, we
All right.
start.
Okay, so let's
Yeah.
go ahead and get started. Thank you, gentlemen, for joining us here today. we handed out the rubrics and a calculation sheet, so I'm really glad that we made it this far. I know there's a lot of annoying emails that I sent out, but let's get started. So I'm Vineet Nair, this is Devin Rowland, Angelica Watson, Ivory Sarsenio, and Matthias Kipler, and we are here to present our deployable sprayer frame.
So I'm just going to start off with giving a brief project overview. So before I actually begin with the purpose of our project, we want to go over like what the current process is. So currently, there is a detection method that is used at ITRA that uses an agentase or a disclosure spray that reacts with certain chemical warfare agents such as nerve agents, GNV, and others. So the way this is done is warfighters manually spray down the vehicles. They wait for the agentase to react for about 5 minutes, and then they go around and look for the contamination sites. And if any contamination is found in the vehicle, it is sent off to a following decontamination process where the entire vehicle is now considered contaminated. So the purpose of our project is to automate the manual labor portion of this, so the spraying of the vehicle, to reduce the potential exposure of the warfighter. So we want to reduce the proximity of them and the possibly contaminated vehicle. Also reduce the amount of time spent on both the spraying and the mapping, and also to potentially save money by reducing the amount of chemical waste that is produced from this procedure. So our biggest objectives are to automate the spraying process, to detect and map the locations of the contamination sites, and therefore reduce the amount of chemical waste, and to design a device that can be transported from one location to another. So in order to basically meet the objectives and the purpose, we want our prototype to demonstrate the following requirements. So we wanted to be able to spray a 2-meter squared area and detect any sites that are larger than 10 centimeters squared. We wanted to save the locations of these contamination sites so that it can return to these later in possibly a follow-up procedure for decontamination, so we can pass on this data. And then we want this to be portable, so we don't want it to exceed 150 pounds. And we want it to be easy to use so that people actually would want to use this. So we want the training time to be under an hour, and we want the completion time to be within 10 minutes. And more importantly, we want repeatability of results. We don't, want one child to say, okay, this child found 10, and then the next time it found only 8, right? We want the same amount each time.
So I worry.
Yes.
You came up with all this equipment, did you Dropbox or did you?
So this is, yeah, so that's a great question. So we want this to be more of like a proof of concept. This isn't going to be something that we're designing to go straight into the contamination fields, right? So this is something that we're starting off small first, right? We want to demonstrate its ability to spray, at least the side of a vehicle and accurately pinpoint those locations so that we can follow up for the decon stage. But it's definitely not meant to be like a finished product.
All right. So again, I'm Matthias Kipler. I was the design lead, so I was kind of the CAD guy. You guys might have seen. Actually, go back. You guys might have seen that before. That was the rendition on the PDR. And you have. I'm going to explain all the subsystems that we got going on and how they work. So, all right. So approximately overall size and dimensions are. We have a 2.2 meter long frame. It's about 1.5 meters tall, and it's about half a meter, a little more than half a meter deep or wide. And approximately, if you want to get like a real life approximation of what that size is, I would assume this whiteboard over here to be about 1 meter tall and 2 meters long, give or take a little bit. And here you can see it next to a military Humvee, so it's a little bit of scale for you too. And as far as the weight, we approximate it to be about 115 pounds, which is under our 150 pound limit. And the way we approximated that is that we actually used in the CAT drawing we use and the CAT design programs, we can actually input all the materials like the aluminum, the metal, the steel bars, all that, the plastics, essentially all the components, and that outputs a weight. Now, that weight was about 90 to 100 pounds, but what we did, we actually increased it to 115 because not everything is in this CAD design. We still have like the pumps, there's some electronics, there's some components like bolts and nuts that are not in the file. So we need to accommodate for those. So we expect it to be at around 115 pounds, 120 pounds when it's all said and done. All right. So for the frame assembly, this basically is what is holding everything up. It's a aluminum construction. It's actually 6061 aluminum, which is widely used in the engineering world. It offers, it's pretty strong, it's pretty light, and it's also not that expensive. So it really ticks all the boxes for us. On the frame, you can see this top beam here and this bottom beam. There's going to be the actual bearing rail. It's going to be on those two beams. This rail is what the bearings ride on, side to side, and allow that the other assembly gets mounted to these bearings, and that's how that moves essentially from one side to the other. There's not going to be any welding. We're going to try to actually just bolt everything together. The reason we're doing that is because whenever I'm not sure how familiar you guys are with welding, but whenever you weld something, you actually distort it. So if we say weld this joint over here, it might create some distortion, and there might be a discrepancy in the actual size of the frame. And what that's going to do is it's going to pose a problem for the rails. The rails have to be perfectly parallel to each other. So if they're not, it'll just essentially jam or it'll create some problems. So we want to try to keep that as parallel as we can. So that's why we're not actually welding this frame together. All right, so next slide. All right, so this is the horizontal motion assembly. This is what it's going to power, the movement side to side, the lateral movement. It's two NEMA 23 stepper motors. I'll get into what those are in a couple slides from now. It's a belt-driven system, and basically the way it works is it's pretty simple, really. You have a stepper motor, so you have two of them, one at the top, one at the bottom. One drives the top gantry, the other one drives the bottom gantry, and then this belt actually extends all the way around, and it clips onto this bracket right there. It gets tensioned by this tensioner at the top. The tensioners, these components are kind of just mirrored. So it's the same thing you have up here, you have down here. And that's how you tell the stepper to move one way. It'll move all the way to the right or the left, and they'll operate simultaneously. So again, fully supported linear rails. What that means is that the rails are supported, they're bolted to the frame every 150 millimeters. So that's it's going to allow it not to sag and to stay on the frame. And also one thing I want to mention, the cable management, it's not depicted here. The reason is because it's very complex too. I don't know if you guys know what a drag chain is. It's essentially a chain that it's, the sole purpose of it is to just run all the wiring. And it's really complicated to just create it and draw, but it's a commercial off-the-shelf part. It's nothing we really designed. We just adapted to the size we need. And we're gonna have one drag chain running horizontally and one running vertically.
How do you assume that both move at the same time? That the top assembly and the bottom assembly transit at the same time?
They're going to be driven by the same stepper motor driver and the same stepper motor controller. So it's not two drivers running them simultaneously. It's one driver running both motors at the same time.
Okay.
All right, so this is a vertical motion assembly. It's one of the more complicated parts, but it's essentially the same, only it's not a belt-driven system, it's a lead screw-driven system, and there's a good reason for that. Basically, just so you have these two rails, which are just to provide the bearings, so it can ride up and down smoothly, and then this in the middle is the lead screw. This is just a long screw that every time it spins, essentially moves the gantry up or down by 2 millimeters. And the reason we're using a lead screw and not like a belt system like on the side-to-side movement is because we want to actually, whenever the motor's not spinning, we don't want this to just come falling down. If you have the belt system, gravity on the horizontal side of things, gravity's not acting against you. On the vertical side of things, it is. So if this would be a pulley system, as soon as this stops this motor up here stops spinning, it'll just essentially come back down. And we want to hold that location, so that's why we use a lead screw. So we have the same NEMA 23 motor, so the same motors for all axes. And then this is the actual sprayer enclosure. I'll talk about that in, I think, the next slide. And the last thing is, one problem that we need to account for is the fact that the motor and the lead screw, they're not very light. So they're about, the motor is about 400 grams or so, and the lead screw will be estimated to be around 500 to 700 grams. So that's significant on these brackets, because we are going to 3D print most of the components we manufacture. We're going to try and 3D print them. So what we're going to do is we're going to use, instead of just the top bracket to be holding the weight of the lead screw and the motor, we're going to share the weight with this pillow. It's called a pillow bearing. It's essentially just a bearing with two bolts. Gets mounted on this bracket, and this bearing supports some of the weight of this lead screw, as well as the motor, because those two are connected with that. The piece in between there, it's just a coupling link. And then you just have the bolts that connect. These brackets will connect to the bearings on the horizontal, and that's really how the motion of the system is gonna be provided.
So are you 3D printing those for prototype, or is that you expect those to be final?
We expect it we expect to 3D print with a couple of different materials. There are certain materials for 3D printing that are, believe it or not, really strong, and we believe that they're strong enough to hold these gantries up. We're doing some testing with PLA. We're probably going to be doing the final product in ABS, which is the type of plastic, or there's other stronger materials. It's just balancing the cost versus the.
And that's what I was wondering is for these types of devices or pieces, components, you do get a cost advantage for 3D printing and just machining them, because it looks like you just have a series of holes.
This bottom rack is a little less complex. The top one is a little bit. There's a bunch of differences in heights for the bearing mounts and for the actual bolt holes, the motor system. It's kind of like they're not very easy geometries.
Okay.
And we're also limited on we have some milling machines. However, if we're going to outsource to a CNC mill, I believe there's one in the machine shop in this school. But we don't know how to operate a milling machine. We can probably ask one of the directors to help us with that. However, if we can just 3D print this, it'll cut down time that we spent actually coming with that bracket.
Okay. Well, that was part of my question too. I mean, it's all a matter of cost.
Yeah.
And I don't know how long it takes to 3D print versus.
Yeah. So 3D print, the cool thing is you essentially tell the machine to do its job, and it takes a while. Yes. But while that machine is doing its job, you can work on something else.
Yes. You also. Oh, sorry. Go ahead.
Those brackets, a major concern we have with many of the projects, by the way, is the students either aren't availing themselves of the opportunities to leverage their coursework, or maybe their advisors aren't making them aware. Why not analyze those brackets in FDA, and then determine what manufacturing process is appropriate?
Yeah.
The other reason that you're probably not going to want to use 3D printing is I thought the reason you selected the gantry device is you wanted precise positioning and holding and tolerancing, which you don't get with the 3D printed nonsense. A precision mill part made of aluminum would be almost too perfect for this, despite having to send it out to be made. But in any event, what you'd want to do is this is an opportunity to actually design and analyze something, and not just draw it up in CAD and 3D print it.
Absolutely, yes.
Now, if you've done the design and the analysis, and it shows that at an ABS, whatever 3D printed plastic, it's sufficiently strong, then it's far be it for me to criticize the decision to 3D print it, but not after the fact.
Yeah. I guess our main concern is keeping time in our heads.
Yeah, but I got to tell you, that wouldn't be very much money to have that sent out. It's probably a few $100.
Okay. Yeah.
I'm glad you mentioned
It can be
that.
done in Manassas.
that's something we can definitely move forward with. FEA can just be done in our CAD software. All we need to do is just set material properties, fix the distance, and the constraint class, and we will.
What a perfect 5 or 10 page report as a progress update to show that the brackets are sufficiently designed and analyzed, right?
All right, yeah.
So,
Okay.
yeah, next slide. So that,
This actually, this is it's also gonna be 3D printed. We expect it to be 3D printed. It's gonna take a lot less weight. It's not like the gantries. So, this is pretty much just a basic mock-up of what you're gonna be looking at. You're gonna have the camera located, this is the camera, it's gonna be located up here in the top, and then the nozzle is gonna be located in the bottom there. The reason being mostly, we're spraying something with either agentation or water, whatever we're using, and we want that spray to drip down and not into the camera. Yeah. We also have a cap here that's gonna get bolted on this. That's just an acrylic cap, and just 5 screws, just to further proof, because also this is not gonna be too far from whatever vehicles it's getting sprayed. So there might be some spray back, might be some wind, stuff like that, that can just actually get water in there, and we don't want any type of water damage. So that's one of the things we're fighting. The biggest things we're fighting is really leaks and stuff like that. So we want to be cautious of that. And also one thing that's not depicted in here is that we're using a solenoid for the spraying system. I'll get into that in a couple of slides. It's going to be located in this pipe. So this is your nozzle, and the solenoid is going to live right in between that. It's just nozzle is the solenoid is essentially a valve that just opens and closes. It's a electromagnetic switch.
Now, all these parts that you want to 3D print, those fall within the ranges of what the printers can produce?
Yes, yeah, actually, I 3D printed this cap, which is,
okay. I wasn't sure how big the parts could be.
It's not that small, yeah.
Okay.
How concerned are you about the fluid coming back at you and impacting the motors or the lenses or frame or everything?
I mean, it's operating at 40 psi, so it's not insignificant, but it's also not outputting a ton of water. In this 2 by 1 section, you're essentially depositing about half a gallon to a gallon of fluid, which is a pretty big part. So we have it in our minds. It's not our biggest concern. I think a bigger concern is having leaks within the system. So minimizing the fittings, less places you can have leaks, stuff like that.
Testing would help.
Yeah, exactly.
Qualify them.
Mm-hmm. Yeah. I think we can go to the next slide here.
I'm sorry, so are you doing actual mapping of this as
Yes.
well?
Yes.
Okay.
Yeah, I'll get into that a little bit.
Yeah, sorry
And
to
then
jump
Ben
ahead,
will-
but I was wondering, so are you using the stepper motor counts as your positioning?
Yeah, that's one way to do it, exactly.
Okay.
Mhm.
Do you have a reset function or
We have a limit switch that will.
Yeah, so I'll explain that in a second. It's essentially just a limit switch system and the way it's going to home and all that stuff. So for the fluid system, really quick, the way it's going to work, we have our pump, our solenoid, and this is a relay board. Basically what we're doing is we're powering the pump through a relay board. Our main computer that runs the whole mapping and moves the motors, essentially, can't power the pump. It doesn't have an output strong enough. So what we do is we have a relay board. The computer will signal the relay board to trigger, and when that triggers, it'll power the pump. Same with the solenoid. Because this works at 12 volts, that works at 12 volts, but the computer only outputs 3.3 volts. So it's not going to power this pump by itself. So we have this connected to our main power. That powers the pump. Once the pump is turned on, it'll build pressure. The reason why we have a solenoid and not just the pump is because we want the spray to begin as instantly as we can. We don't want the pressure to slowly build up and then the spray do its thing. So that's what we do with the solenoid. Essentially, the solenoid is as closest as the nozzle as it can be, and then the pump powers, pressures the system, solenoid opens, and it sprays. I think that's good for the slide. We'll move. Okay. So stepper motors. As you said, yeah, there's 200 steps per revolution on these motors, and that's how we keep track of where are we at.
These are NEMA 23 stepper motors. That's just the naming convention for the motors. Basically means that this faceplate is a 2.3 inch by 2.3 inch faceplate. These are pretty strong
Motors
motors.
for our application, we don't want it to be, we could honestly went with a NEMA 17 for instance, but we want to be sure that it can move that big entry and not have any problems that way. This is the driver. This accepts the 24 volts that this motor runs on and feeds that. Whenever you signal this driver to work, it tells the motor to work. So essentially move forward, backwards, or turn the other way. And also there's another component that we're going to use. It's either an Arduino or an actual CNC controller board. So it's a controller for the stepper.
And the reason being is just that, well, actually, Vinny will get into that later.
Yeah, that's about right for the motor. Oh, I'm sorry. Go back. One thing I forgot to mention. These are actually open loop motors. They're not servos. So what that means is that the computer has no idea of the location of this motor. If you just go ahead and turn it, the computer's not going to know it's been turned while it was powered off. Now, there's a way we're going to go about this problem. Because the thing about a servo is that typically for these applications, they're quite expensive, although they might be, and they're also different. The way you drive them is completely different. So we need to think about different powering systems and different microcomputers to power the servos. So I'll explain how we're going to get around that problem of having an open loop
System. All right.
you can go on. So commercial to shelf parts and specialty parts, as we said before, anything that's going to be manufactured, we expect it to 3D print. Stuff like materials is going to be, of course, commercial to shelf. The purchasing of aluminum is going to all done through the same website.
Trying to find a reputable website that can provide us with good quality materials. Again, the 6061 aluminum sections we're getting, we need those to be as straight as possible. So getting good quality materials is really important. And these come in 72-inch sections that we're then in Manassas going to cut. There's a bandsaw available there. So we can use that to manufacture and build our system. And then tensioning pulleys, all that's going to be 3D printed. Camera spreader module is going to be 3D printed as well. And yes, that should take care of that. All right, so there's actual video.
I'm going to show you guys in the next section. Hopefully that will clarify anything that I can't explain it well enough here. So again, this is not a closed feedback loop system, so the computer doesn't know the location of it. So the way we're going to get around that is we're going to use a limit switch system. That's just essentially a momentary switch. That's really all it is. And it's going to be located at that bracket. So it's going to have either one or two or four. So one per axis at least. So we're going to have one on the bottom and one on the right side. And what that does is essentially the computer will start. It'll tell the sprayer to actually find its home location. And what that's going to do is just going to travel down. It's going to find its home location. When that limit switch activates, it'll know it's at the bottom part of the sprayer, and then it'll move to the right and do the same thing with the other limit switch. And when both of those things happen, it'll know that it's at the corner of the frame, and it'll essentially be able to tell how far to move this way or how far to move up without actually crashing the machine. And actually, let's try to go, and this is what I mean with calibrate at the startup. It's essentially homing.
Let's see if this video plays.
So here you see it'll travel down. This is starting up, finds the home there, travels all the way to the side, hits the limit switch, finds the home, and then it does its spraying procedure, which is just going to be a different couple sweeps that it goes through. In this case, it's just 3 sweeps. And once it's done doing that, it should be able to just directly go back to its home position.
Yeah, it's very nice. You're not relying on a lot of exotic software
Exactly.
to control. It's
Yes.
It's a dumb, robust switch.
Yeah.
It's very nice approach. Yeah.
So that's pretty much that. It's pretty simple demonstration, but it's simple. We want to keep that in, simpler we make it, the less problems we're going to have in the future.
All right, so that's really the design.
That's fine. Do you have any questions?
Yeah, 2 items. One, would you discuss power management for us, please?
I think, Benny, you're going to discuss.
We're going to
Is
discuss
that
that.
covered?
Yeah,
All right, I'll hold that question. In all of the frame aspects that you talked about, what is the relationship between we're going to buy the materials, we're going to bolt them together, blah, 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 versus going to a contractor and say, here's my design, here are the tolerances, this is the type of material I want, you guys go buy the material and put it together. Or it sounds to me like you are almost 100%
You're gonna build.
is that
Yeah,
true?
so if we're gonna do 3D printed, the cool thing with 3D printing is that the rapid prototyping.
Yeah, I got that part, but
So-
I want you to do cowboy engineering where you 3D print 452 different versions and you get one you like.
Because not that we haven't seen that before.
Not that we haven't seen that before. So, but am I correct that damn near everything is going to be assembled, manufactured, fabricated by this 5-person team?
Yes.
Yes, that was it.
Okay.
Well, most of their stuff's COTS.
Yeah,
I hear the cops, but
it's just, I think, 5 or 6 parts that are just these brackets, these tensioners.
The faceplate for that camera and the enclosure, and just the motor bracket.
and the integration of the control systems and everything else takes time.
Yes, that, exactly, that's why we're trying to do, make that's also why we kept the frame as simple as we can. It's really not that, complicated of a part, so we expect not to take too much time actually building the frame, and more time actually developing, like, processing and programming, right?
I guess it's drawn to somewhat the scale. If that's the case, I don't know where the center of mass and what the weights are. You may want to look at the stability of the frame.
Yeah, so
Like both
it's
sides weights
pretty,
and both
it's
sides.
pretty, okay, yeah, I see what you're saying, but it should, everything is in a single plane, so the
Yes.
center of mass is, it's in between these 2 beams, which is about half a meter long.
Just as like.
Yeah, I would still do the tipping
Yeah, absolutely,
analysis to
yeah.
make sure that those outriggers.
It looks like pretty skinny and pretty.
That might be a perspective though.
Yeah.
Yeah, this, by the way, this is the perspective is for one of these CAD programs that.
Yeah, okay, that's what I was asking.
Yeah, and
It
then we
would be
might
very
send it to
embarrassing
you.
if it toppled over when you turn it on.
Right.
Absolutely, yeah.
Bam! Also, I think what it is, what is the pressure of the nozzle when you get
Yeah,
out? That
right,
that's what
right.
pushes you back.
Right, yeah, back
Then you
pressure
don't
stuff.
take that, not just the weight.
Loss.
Alright, so I think,
And
now we're gonna move into.
before you go to the rest,
Yes,
I thought at the start when I read the scope, I thought you're going to spray underneath the vehicle. It looks like you're only going to.
no, we're just doing, we're working the sides, I believe that the other D2 team.
Okay.
Yes.
Team A is deciding to focus on the undercarriage vehicle.
Oh, right, a little divide and conquer that.
I thought you guys are doing the same thing.
Yeah, very well, that's good.
One vehicle the next hour, yeah?
Yeah, good, we'll stick around.
If there's not any questions.
Well, I do have a question about
Yes.
mapping.
Uh-huh.
How did that, like the drag train, is that what makes it accurate?
Excuse me, the jack chain?
Yeah.
No, that's just to provide a cable management, for we don't want anything to kink or break. The mapping is essentially gonna be after the spraying procedure, once the agent taste, actually finds whatever contamination it finds. There's gonna be another sequence that is gonna go, and I think Vinny's gonna explain it a little bit better
We'll
later.
talk about that in our
That's
project.
gonna just take the pictures.
Coming up.
Yeah.
Hi everybody, I'm Angelica Watson and I will be going over the project risk. So we all know that risks are subjectible, so as a team, we came up with a ranking scale that will rank our risk from a high scale to a low scale, and they will have numbers, so 5 will be a high risk and 1 will be a low risk. And as a team, we want to be able to identify and make sure that we can know where risk can occur and just be prepared for them if they decide to happen. With that being said, I will jump into our first risk, which will be the fixtures of our support of the deployable sprayer frame. You guys were just talking about that, making sure that our legs are able enough to support our system with our rails and making sure that it's not too heavy, and if it is too heavy, we want to make sure that it does not deform our parts. And with that being said, we're going to choose the aluminum 6061, so we're going to make sure that's a durable enough steel that can support that load. And also just making sure that our dimensions are correct for when we have our legs, that we can account for it if it tips over. The next one will just be the sprayer. And our sprayer system, which consists of we just pass it around, so it'll be having like our camera and our nozzles. If that sprayer system is too heavy, then it will cause our motors to overwork. We put this as a low risk due to the fact that we chose the NEMA 23 stepper motors, and they're more than capable of getting the job done, but they're just heavy duty, so they won't too much like not work if our sprayer system is too heavy. And then with that being said, because the NEMA 23 stepper motors are pretty heavy themselves, and we're going to 3D print our brackets, we know that that's a risk. It's pretty moderate, but we're going to use the materials PETG or ABS to choose which material may be better for our system. We know that's changeable, so that's why at a 3 is not as a high risk, because we could just go out as Professor Lucen has said, go out and try to get a part manufactured because that's nothing new to us, or we're just gonna change the material of our 3D printed bracket. Also, another risk that's gonna rise is tubing kink. With that being said, tubing kink is more so like a manufacturing area where we purchase our tubing. It could be a small hole or just bends in our tube that will cause a loss of pressure. Yeah. That will cause a loss of pressure. And we put that pretty moderate because if that does happen, we can go home and buy new tubes for our procedure. Another risk that's pretty high on our list is the poor connection and leaks. So with that being said, when we're trying to assemble our fluid delivery system, hooking up our tubes to our fluid delivery system, if anything on our end, such as human error, not making sure that it's tight, making sure that our fittings are correct, we can have leaks that occur that can mess up our system. So we're just going to try to minimize that error and making sure that everything is tight, make sure we don't design fast, and making sure that everything is secure before we start to add the power and make sure that our fluid is correct. Also, with that being said, because of our sprayer and our pump, we can have malfunctions with that. Due to the fact that we're going to use a solenoid, if that solenoid doesn't allow for our pump to build up enough pressure, we can come out when we start to spray it on our system. It can be unevenly sprayed or just patchy, and it's not enough agitated C2 that would be covering our machine, so we can have possible risk of not even catching contaminant, which would lead to a bigger risk of letting our vehicle be passed to a safe zone when it's actually not. We also know that we are going to have electrical component. Next slide. Electrical component risk. Water damage is like the main biggest risk that we know we will be facing, or just any type of fluid that's getting into our system. Overall, we know that the water or the fluid can damage our whole system, making us start our whole circuitry project over. So we know that's a big risk, and we want to be aware that it could possibly happen. One way that we're going to try to minimize that is just making sure that we minimize our fittings and making sure everything is more tightly secured, just so we can avoid that. But we still know that's a high risk and it's going to be there. Another risk is the power management, which will be from our batteries and our power system. Due to the fact that we're probably going to have a couple of batteries in our system, the main thing that could probably happen is just overworking of the battery, and it will cause our system to shut off. We won't necessarily destroy our system, but more so just we would need to reboot the system. That's why it's just at a moderate risk compared to like the water damage risk, because we won't necessarily have to start over, but just probably restart that process if our battery decides to fail. And then with that, we can also just go buy more batteries with higher voltages that are needed.
Where is your circuit board, your control arm system relative to?
It's not on the frame. It's going to be to the right of the frame in a separate box, and everything's going to get routed to the sprayer.
Oh, so it's not riding.
It's not riding. No.
Is anything riding besides the solenoid and the
solenoid, camera, and sprayer wiring leading up to it?
The pumps, those are all
That's
off.
Yeah,
it's all going to be
The
tethered to
batteries
the
are all
side
off board.
Yeah.
Maybe to, boy, Nathan's got a lot smaller. Maybe to Nathan's point, if those were integral to the connection from the base to the vertical support and put them here, maybe they add weight and would support, having reduced risk for tipping.
Yeah.
And also,
You got to put them someplace.
Yeah, exactly. We were thinking about clamping them to one of the side braces on the pretty much exactly what you mentioned.
Don't go up.
No, you don't want to keep the center mass low. Yes.
But if this is not battery powered, by the way, it's going to be tethered to a output source.
Oh, AC.
Yeah, we're actually going to mention that very shortly for the validation aspect.
It's a
Running on a power supply. You had a question, sorry.
no, I'm just going to comment. I mean, to me, that's one of your key mitigation of risk is you can seal that off multiple times. Wrap it up really tight, effectively, so that there's going to be mist, etc. But I mean, to me, that's the number one. I mean, proximity matters. So the fact that you've designed it to remove proximity to some extent, that ought to be something that you highlight.
Probably another risk about
Next slide.
making sure the plugs and everything are far enough removed.
Going on our last risk, which is very high, which will be our programming and mapping, due to the fact that we are not software engineers and we're really not that great at coding. We know that a lot of time will be spent into learning how to program our system. Programming will come into effect with our locating of our contaminant. So So being able to map our coloration and go back through it, we will need to make sure that we take enough time to learn how to develop our software, learn how to code it, and learn how to be able to locate where a contaminant is being, where a contaminant is located. Also, programming comes into play when we're trying to move our stepper motors. So with that, we're going to try to incorporate the limit switches so we know where our sprayer is at and where when it hits the end, it needs to start over. In case that doesn't happen, we're thinking about incorporating a stop switch. Well, if we manually see that our system is not going back to our home reset button, then we need to manually stop it because it will just be crashing into the ends and not knowing to return home. So just making sure that our programming and our timing is very efficient because we know this will take up the most amount of time of our project because it's so highly dependent on it. And that wraps up project risk pretty much. And I will hand it over to Vinny.
Okay, so now let's get started with our project verification and validation. We just talked about our risks, so we're going to say how we're going to mitigate some of our risks. And the verification and validation is showing how we are going to verify the design requirements that you guys gave in our house quality. So here's our diaphragm pump right here. Our pump operates at a pressure of 40 psi at a gallon per minute. 40 psi is standard for most spraying applications. Sprinkler systems, 30 to 40 psi. So that's the pressure we decided to use. Although when we took a look at our nozzles actually operate at 40 psi, but can only supply a flow rate of half a gallon per minute. So we're going to design to half a gallon per minute. Right here is a little conversion from gallon per minute to meters cubed per second. And I often like to refer to customer units to give a better visual representation of how much fluid is being dispensed in a given amount of time. Here we have our fluid speed calculations. So we know that the fluid flow rate throughout the system, the volumetric flow rate is going to remain consistent throughout the system. The fluid coming out of the pump outlet is going to be the same as the fluid coming out of the nozzle outlet. So we're dealing with an incompressible fluid, constant density. We know that our flow rate from our previous slide is this value right here. And by just converting our 1/4 inch diameter section of the hose to millimeters, as well as our 3/8 diameter inch to millimeters as well, we just did a simple area calculation, pi times distance squared over 4. And you can see we rearrange equation 1 to solve for fluid velocities. This is the speed of the flow, 0.4426 meters per second of the flow inside the tube, and then 24.91 meters per second is the fluid velocity of the water coming out of the nozzle. Our volume flow rate is going to be verified using a simple bucket test. We have our 4-quart reservoir. We're going to time to see how long it takes to fill these 4 quarts, and then from there we can verify our velocity. So nozzle bandwidth, that's where we get to our nozzle calculation. So we decided that our nozzle is actually going to be placed 50 centimeters from the spraying area. So essentially what we did is we're going to do our nozzle testing. We selected 4 different nozzles, 30 degree, 50, 65, and 80. And it's important to note that these angles are actually that total angle right there, so we have to divide it by 2 and then use a little bit of trigonometry to find that height distance and then multiply it by 2. That gets the bandwidth or the total spray coverage. Now what you're going to start to see here is with the wider the nozzle, the more coverage we're going to get. With the smaller the nozzle, the more amount of passes we're going to need for a sprayer frame to completely cover that 2 meter square area. So based on the house quality that we filled out, some of our customer requirements was that we had to complete this process in 10 minutes or less. It's got to be a fairly mobile system and have an accurate spraying ability. So that's where our horizontal speed comes into play. We decided that we are going to be using 1 gallon. So if our flow rate is half a gallon per minute, we're going to be spraying for 2 minutes total or 120 seconds. So what we did was we had to calculate the number of height changes according to table 2 right here. We divided our 1 meter height distance by our spray coverage and rounded to the next highest integer to get the number of height changes we need for our entire spray area. So what you're going to start to see is with the larger the nozzle, we're going to get more coverage so it doesn't need to move as high. With the smaller nozzle, it's going to have 4 height changes. Then from there, what we get is our number of sweeps. So we are going to multiply the number of sweeps by the 2 meter length distance and then divide it by 120 seconds to get our horizontal speeds right here. Now for 3D printing applications, printers move at 40 millimeters a second, so that would actually fall in between this range right here, 0.04 meters per second. So we know that our sprayer frame isn't going to be moving as fast as a bullet train, nor is it going to be moving as slow as a snail. But our speed ultimately depends on the type of nozzle we select. Now we'll get a little bit into our vertical speed calculation. Vertical speed is important but not critical to our overall design. Our vertical speed is essentially a function of two things. Our lead screw pitch value as well as the rotations per minute outputted by the stepper motor. We decided that our frame itself is going to move 1 meter upwards in a minute. So we can design, we chose our velocity, we can design according, we can set the amount of rotations per minute for the stepper motor. What we have to do is, if we want it to move faster, the RPM is going to go up, otherwise it's going to go down. So again, this goes along with the height changes. We want to do this in 2 minutes. So it's going to move across, and then it's going to move upwards. That time is what we're talking about right here. And then both our vertical and horizontal speeds are going to be verified with a timer. We're going to just time to see how long it covers this distance.
When you start this, is it spraying continuously the entire time, or is that controlled?
It stops at the ends. When there's a height change, it would stop.
So there's no spraying going on in vertical motion.
Oh, okay, so just the pass.
Just horizontal.
Okay.
Yep.
And something also important to note is with our 80-degree nozzle, we're going to see a little bit of an overlap or an overshoot. What we can do is we can design our starting point to see where we want our sprayer to start to make sure we get no overshoot, and overlap is good. Next slide, please. Let's get a little bit of power consumption. So we're working with a 24 volt, 25 amp, 600 watt power supply. Our power supply is actually going to be bolted to the frame. However, we are going to have it tethered, and we're going to be using a power meter to test the wattage for each individual component and make sure it does not exceed our 600 watt. Let's get a little bit into the brains of our operations here. So we have our Raspberry Pi and we have our Arduino. Our Raspberry Pi is a microcomputer just like the computer you see in front of us. It has a Linux-based operating system, and it has a multitude of tasks to worry about. It has to worry about the sprayer application, it has to worry about the mapping as well as the scanning, which is why we are using our Arduino for our stepper motor control. It already has too many tasks to worry about, so that's why we have the Arduino, and it runs on a loop, and our Arduino will then communicate to our Raspberry Pi. Oh, and then also, like Matthias had said earlier, our Raspberry Pi has 3 general input-output pins that can only output a voltage of 3.3 volts. So that's why we have a relay board. It's capable of accepting a low pulse signal and then amplifying that voltage for the necessary pump and solenoid voltage for 12 volts. Now, contamination detection, that's arguably one of the most important aspects. We are going to be using ImageJ. It's an image processing program to locate our contaminant. It's an open source software. It runs for Linux, Microsoft, and what we're doing here is we are going to identify pixels in our sprayer frame. So just imagine we have completed our spraying process in 2 minutes. Now it takes around 4 minutes for our agent taste to completely react and have this red marking. Once that's done, we are going to have red pixels separated from the color of the remaining background, and that will be able to isolate where the contaminants are actually are. Scanning and mapping, so we are going to be using Python for our Raspberry Pi. We decided we're going to use a version of C for our Arduino. So say we do our spraying process, and then after it makes the amount of passes it needs to make, it will hit the limit switch and return to home. Once that's done, we are going to take individual pictures and make a grid essentially. So the picture size is going to be dependent on the camera view angle. So what we're doing, say we make a 5x5 grid. each individual picture taken, this will have a location assigned to it. So this, say, will be 00, 01, 10, 11, etc. So once this is completely done, ImageJ will communicate to a Raspberry Pi where the contaminants are based on the location we chose for the grid, depending on the grid size. Now, once this is done, it's going to return to home, and then we're going to have another function that's going to communicate, okay, so this is where the contaminant is, this is where our camera module needs to move to effectively mark our contamination site.
Okay. Thank you, Vinny. Once again, my name is Devin Rowan. I'm
Hang
going
on
to
for a
discuss.
second. Cool. So you're gonna have to baseline ImageJ for the background of whatever vehicle you're looking at.
Right.
If it's Desert Camo, you got one. If it's a different vehicle, you got another.
Right.
And then you're gonna have to communicate that to the system so that it knows if it sees a bad spot.
Yes. Yes.
How do you do that?
So we have to do a significant amount of research for ImageJ. We do know that several risks might occur. Say we're looking at a vehicle and say there's a red sticker. We need to be able to know, okay, the red sticker is not the contaminant. We need to locate the contaminant as well as several other factors.
How are you gonna do this?
Well, hold on. Is the requirement to apply the spray, wait for it to change color, and do the image analysis in 10 minutes? Or is it just the total time is the application of the spray, it changes color, then the data is taken, and then that takes X amount of time, and then you apply the decontaminant?
So we are spraying in 2 minutes, we're waiting 4 minutes for the reactions to occur. Then the remaining 2 minutes is going to be taking the pictures of the individual grid, and then finally afterwards, that's when we will be communicating where to move it. So we do aim to try and get this in 10 minutes or less. However, we might go a little bit over.
And with the agencies, it is temperature, whatever temperature it is outside, so that all passes through the house.
Right. Right.
That 10 minutes isn't like set in stone.
So I guess I'm not a computer scientist, but in here you're going to collect a lot of data. How are you going to process that fast?
Well, I think that's my question. Is like I used ImageJ years ago when I was at the lab, and you're counting individual pixels by hand. That's the way I did it.
Whoa.
Because I was looking at like corrosion pit depth and stuff from impingement tests, and the areas are very, very small. So I don't have a feel for how quickly it takes you to, like, if you had an image on like a 1 foot by 1 foot grid, essentially, how long does it take to kind of at least get an outline of what like that overall area that's contaminated, like at least the boundary of it, say? I have no idea how long that takes.
About the work that was done 2 years ago.
Yeah, there's a lot of parallels there.
Right, so a couple of years ago, we had a corrosion detection capsuling project. They used ImageJ to capture and determine corrosion, depth, pitting, the whole thing. Perhaps that could be used here to, kind of march down the road quickly.
Yeah, I think
for
everybody had-
image processing.
Everybody had trouble with the depth on that,
Their
but
problem
the
is
color,
much easier.
the color change, so I think it's viable. I mean, I'm not pretending that I can sit down and do it, but I think their approach is very sound. I think what you want to look for is the color change, and then only do well, it depends on which faster, but do you subtract your baseline from everything and then look for the color change, or do you just identify a color change and then see if there's anything that
We plan on identifying the color change and returning the location of that exact color change to provide location of the chemical contamination.
So your intention is only for detection, not decontamination. Then 10 minutes or 15, once you detect, you can send it back and go.
Well, so according to the House of Quality, the customer's #1 requirement was to locate the chemical contamination, and lower down, I think it was number 3 or 4, it was actually decontaminated.
Yeah, but
What
what I
I'm
meant
saying
was-
is, how do you know where that is as opposed to a sticker on the vehicle or the underlying color of the vehicle material?
Well, with the Agente spray, it's a very distinguishable color. So it's a bright red
With
color.
the-
So it's
With the vehicle, the baseline picture, so that's how I guess you could get rid of those false positives essentially. So if you can take a picture of everything else, you can compare what's new and what's old. And as far as taking the picture, so you're going to have this grid. Every image is going to be
Input it into the memory.
the Raspberry Pi or main computer. That main computer is going to have essentially a library of all these images. Call it 11 or 001, whichever way you want to structure that. Then that structure, every image will get
Pass through this ImageJ. I'm not too familiar with ImageJ
myself, but it should be available software for us to use. And then
I'm with him, I think it's viable.
Yeah.
I think it's complicated and it takes a long time.
Yes.
To get from where you sit now to using that capability to answer the issues that he's posed.
Right.
Who among the five of you is the ImageJ soon-to-be guru?
What I'm
Let's say all of us.
What I'm
We're gonna
getting
discuss the
at,
plan very shortly.
Yeah, what I'm getting at with this is, I think you could very quickly make this very, very hard on yourselves. And maybe the requirements were not well posed much earlier in the semester. I think it's very laudable that you take pictures and that their post-process is a separate requirement. And I think there just should not be a rigid time on that, because that, I think, to do that in your 6 minutes are just in applying it. I don't think you're going to do the analysis in 4 minutes. So what you want to do is at least get the information, store the information, and then if you guys can sit down with laptops and process some of it in some reasonable amount of time, and if you want to have a reach goal to go back and apply the decon, I think that's fantastic.
But the problem with the customer's requirement is you won't be able to do real time, so you can.
But that's too hard. They don't.
Yeah.
That's too difficult for right now, because I think that would involve significant, extensive programming and to do that in real time. I think it's enough to make this thing work automated as you've done. Spray it, let it change colors, take the images, and then process the data. And if that takes you 6 hours, fine, because it's still part of the overall demonstration that you would then make a decision based on that information as how the decon gets played. But I think let's not make this too difficult on them that in 5 minutes they have to process this basically something like this in 240 seconds. It's just too much.
Right.
I'm telling you my experience. I've done extensive ImageJ work, and it's extremely tedious. And for me to look at something the size of a pinhead would take me all day.
Right.
Yeah. How are you doing this in 4 minutes?
Right. We intend to use some of our slack time to take a look over winter break into ImageJ.
Yeah. So just don't make that too hard. I mean, you want probably when you're mocking this thing up, you want like a nice big target to go after first.
I'm discussing that very shortly.
Yeah, baby steps, right?
Well, I guess for us, it's the location of the red dot.
Right.
Yeah,
That's
which
the-
I think
that's
they
why
can
we
get
wanna
that.
grade it.
They can't get that in 10 seconds.
Well, no, we
Yeah.
thought that.
They can. I think they can get that to you. If it takes them several hours to process the data because you're not data scientists, you're not computer scientists, then so be it.
I guess at the end of the day,
What I would consider the most important part is to have some sort of data outputted by the computer and then analyzed, but having some, as you said, the location. So every image has a corresponding location within that frame. So
And then we'll store it in some sort of array. And then decon, it's a priority, but it's not high on the priority list. It's something we would like to get into if time allows. But mainly marking these sites is what's most important.
What is the typical size of the contamination they can look for? Because they can
Approximately
lower
10 centimeters squared.
That's the small
Can
end.
you lower the resolution of the image when you just make sure it's detectable, but then you
Well,
don't have
there's really no set in stone. It could be anything really. It could be a size, right?
And they get a lower bound, yeah.
Yeah, they have sort of lower bound. So if you think of the corrosion contest, those guys had.
They're like a tiny little.
Right, they don't have, so this is easier.
Well,
than
I
that.
agree, but I think it's so challenging.
They were able to find, manually identify and report
Right.
approximately 10 to 12 instances in less than an hour.
Right.
Because they were doing some of the processing while the other people were doing the operation.
Right.
So I think I think an hour is something that you guys should.
Oh,
should
yeah,
have
I
in
remember
mind.
doing it by hand, and it wasn't that bad once you kind of got good at it. But that's what I'm saying. The task to do that in an automated fashion, or to hit a button, is very, very challenging, right?
I mean, the software was supposed to find it. They did a human check and
Correct.
say, okay, this is
Yeah.
that corrosion. So you guys should be able to have the same thing where the image is coming back and it says, I found a red spot right here, and ImageJ will probably circle it or put a boundary on
Yep.
it for you, and then you can do the manual confirmation.
It's also a plus we don't have to account for depth as well.
Yeah,
We can look
yeah.
at flat surface.
Yep.
So,
Yep.
so I think if they put that on there and it's done and they're in under the 10 minutes, the color changes happen and they've recorded it. That's pretty good for what
Yeah.
you're asking for. And then hopefully, you know, then the goal is how much can I shrink that down? And an hour should really probably be your upper bound.
Yeah.
And then how much can I shrink it down? And then tell my system, yeah, the things that were identified, numbers 1, 4, 5, and 8, go decon. That's-
Or I didn't get anything.
Or I didn't get anything, yeah.
Yeah,
false
that's
or
scenario.
a true negative.
But somebody,
that's a
somebody
tough
on
test.
your team has gotta be the ImageJ guru. Serious business. And we have teams that have used ImageJ in the past, and those graduates are still in the local area if you need some help.
It's not bad. It's not difficult to play with it. And you guys can the good news is you can do that in parallel. You can mock up a sample with some red paint and get the image, take a picture and start using ImageJ, and then you do that while you're building the thing, and after a few weeks you have some proficiency at how to process
So you're
data.
actually discussing what we're about to discuss in the next
Yeah.
few slides, but.
Well, then get
it's all
on
good.
it. What do you?
Okay.
Christmas.
One more time, next team's gonna have to come.
Okay. Oh, wrong direction. Yeah, as I said before, I'm Devin Roll. I'm going to discuss the project planning aspect. So here you see a Gantt chart. These are just providing the milestones for Team CAS in the upcoming spring. So our strategy moving forward is we want to work on all aspects equally, but we do believe in deadlines to maintain productivity and keep us on our toes. That being said, we've summarized the work for the deployable spray frame into 5 major aspects. They are as following. They are the fluid delivery system, the frame construction, the programming aspect, the power management, and developing the mapping software. So the way we came up with this order is by evaluating which aspects are the most labor intensive and require the most hands-on work. That is the fluid delivery and the frame construction. We want to tackle those as soon as possible to provide ample time for testing and room for error, because we all know that no plan ever goes as perfect as first planned originally. Then after that we have the programming, power management, developing mapping software towards the end of April, and eventually we're going to hit the evaluating prototype performance. This just signifies uniting all of the major aspects mentioned and seeing how they satisfy the customer requirements entirely as a whole. So now to move on to the work breakdown structure.
A question.
Yes, sir.
In your team, among 5 of you, do you have one who's expert in programming and data?
So Matthias, as
Or
you
do you
can
need
see,
help?
has great expertise in the CAD developing and everything. But
I
as
like
far
this.
as any specific aspect, it is much of a team effort. You understand? So we don't want to. I mean, we're all taking this opportunity to learn and try to strive and grow in as many areas as possible. That being said, we all want to do a team effort in every aspect.
Well, the reason I asked, they had an offer from another department, the data science analyst, they said they could come and help out our capital
Cool.
teams.
That sounds
That would
awesome.
help.
And offer one body for the semester, but if it works with, let's talk offline, yeah.
Yeah, yes, cool. All right, so you see the work breakdown structure. So this is going more in depth as to our plan of action moving forward. For example, for the fluid delivery system, we gave it a duration of about 7 days. And in that 7 days, we're going to be physically assembling the fluid system, wiring all the system components, and testing for pressure and leakage. So another key factor about this work breakdown structure is that us, Team CAS, we're not going to be able to proceed until the fluid delivery system passes the nozzle spray coverage test and the bucket test. And if you have questions about that, I'm about to discuss that in the next slide. So we're going to hold those tests hopefully at the end of the duration, give or take a few days. Then after we finish the fluid delivery system, we feel it's critical to start assembling the frame. That's going to consist of the frame assembly construction, 3D printing all the components that is necessary, give or take some few we might buy off the shelf. Then we have the linear and the vertical assembly motion for the motors. The test for that frame construction is going to be testing the linear motion, making sure the motors that they're moving in the desired directions that we want them to. Then the second largest chunk is going to be programming. This is 30 days. As mentioned before, we are not software engineers, so this is going to be a very difficult aspect. So we put 30 days away for that, just to make sure we pay good attention to it and file it properly. So that's going to consist of programming the SM controller, integrating the Raspberry Pi with the SM controllers, and programming limit switches. The test for the programming aspect is going to be the home location test and the speed test. Next, we have the power management course. This is going to be 10 days. It's pretty self-explanatory, just making sure that all the components of the deployable sprayer frame get the power that they need to serve their task. That's going to consist of running the main wiring throughout the deployable sprayer frame and testing the component powers and the power test. Last but certainly not least, we have developing the mapping software. We put aside the most time for this aspect for two main reasons. One, as we mentioned before, might sound like a broken record, but we are not software engineers, so this will be the most difficult task for us. And secondly, it is at the top of the customer requirements list, it's at the highest priority. So we really want to make sure that we satisfy the customer with this certain aspect. This is going to include camera incorporation, the J software that we spent a lot of time mentioning, and developing the grid map for the deployable sprayer frame. The paint canvas test is essentially what you just mentioned before, Dr. Knudsen. I'll speak on that in the next slide. And then after that, all the end, we're going to prepare for the final demonstration and have the final prototype test. But now let me go and discuss the test plan. So January 23rd, we have the nozzle spray coverage test. Vinny mentioned this earlier. This is going to be pretty much analyzing which angle nozzle is best suited for our case. We're going to test all the different angle size nozzles and see which one does the best job of covering the 2 meter squared area in 120 seconds. Then go down to January 28th, the bucket test. This is just to verify volume flow rate. The main goal is to reach 2 quarts in 1 minute. So before we proceed, we want to make sure we hit that rate. 11th of February, we have the linear motion test, as mentioned before. Just want to make sure the motors are traveling the desired direction we have. February 25th, we have the limit switch test. This is a little tricky, but not that complicated, pretty simple actually. So it's essentially, we want to have the camera and the sprayer move in the desired path and hit the limit switches at the end. And once it hits these limit switches, it knows that it's done its path, and it wants to return back to home, the lower left-hand corner where the coordinates are 0, 0. That's pretty much so. All we want to do is make sure it does that and go back to home. That's good. Speed test, making sure that the motor travels at the desired speed we want it to. Component voltage measurements and the power meter test. Just want to make sure all the components are receiving the power that they should be to perform their task. And lastly, we have the paint canvas test. So essentially with the paint canvas test, we're going to take a paint canvas like this size, about 2 meters squared, and we're going to blotch it with random blotches of paint and record those values and test whether or not our developed mapping software is going to return those values that we already know and have it written down. And that's pretty realistic to spraying the side of the Humvee or whatever vehicle we're working with our agencies and using the surrogate that we potentially have and having it react and show a distinguishable color. It's going to be pretty similar to when the real case.
That has some independence in there. You don't have to wait until 10 April.
No, essentially, so what I was saying earlier, we want to work on all these as soon as possible, but these deadlines are just to make sure that we're maintaining the productivity. So, good things go happen. We can have this whole thing done by mid-March, but we want to account. We want to,
Fun to be optimistic.
Right. Fun to be optimistic, but here's our best plan of action for this spring.
I agree fully with him. I mean, you can make a paint.
Yeah.
You want to choose maybe different colors and different shades.
Yeah.
And then you can have a still camera and see what.
Yeah.
See how you process that.
I'll use red because that is the color of.
Well, yeah, but different shades, you know,
The
how
different shades as
orange
well,
do
yeah.
you know?
Different
is-
shape sizes as
and
well
there's
too.
contrast stuff too.
Yeah.
Yeah.
Yeah, of course. Like Professor Gallo said, we want to make sure we get the paint, not like any of the stickers, any insignificant
So
spots.
I think early on you did this straightforward calculation, but I can't remember for sure. 1 gallon covers 2 square meters. That's what the prescription is.
Yes, and that's what
Okay,
all
so
of our
that's what everything else is
calculations
derived from.
Yes, sir.
Yes.
Exactly. That's the constant right there.
Now, we do think that, I believe H&T is a 2-phase product. We actually, I might be wrong, but you actually have 2 different containers and they get mixed and then they get sprayed. This is what I think is how it works, so that would be.
Yeah, training one, I don't know if it's like that.
Okay.
So,
Yeah, because we were given a couple of videos, so if that's the case, we would maybe have to have 2 different containers and then mix that, but if we're testing, we probably can just use that simple 1 container, 1 gallon.
All right, let's move on to the projected path of funds. So as you see here is a pie chart of all of our different aspects where our budget's going to go to. We'll start with the largest portion, electronics. This consists of the camera, the cabling, the motor drivers, the controllers, and the lemon switches. Next largest we have the raw materials. This is going to be our frame materials, the 3D printed components, such as the brackets, the camera enclosures. And then next we have the system mobility at 29%. This is going to consist of the motors, the lead screws, the belts, and the pulley tensioners. And last but not least, we have the fluid delivery system, which is just the relay boards, the pump nozzles, and the sprayers. That all adds up to about $1,150, so we're good on budget as well. A lot of room for whatever needed repurchase things. Not that we anticipate on that. All right, that concludes our critical design review. We thank you guys all so much for your time. But before we proceed, any other burning questions you guys have?
the power, it says on,
Tethered.
it's like a generator or?
It's a power supply, so it's 600. It's essentially just outputs 24 volts, and then we're going to have step down transformers to actually power
It
all
could
the
be a
different
generator, given
components.
that this is going to be probably outside and in the outdoors.
Right.
But you're plugging it in someplace.
Yes.
Yes.
So they make pumps that go into fancy fountains, right? That are used to being underwater, and they have to have power to those, so, you know, that's not technology you have to go invent.
Yep.
But you definitely have to be concerned about the proximity of water and the fluid
Of course.
and electrical.
That'll come with the leakage testing and the pressure testing.
Yeah, and it only have a gallon of fluid, right? So it's
Right.
Per
not-
run, per test, yeah.
Yeah, it shouldn't, even if it springs a leak, you know, they should be able to shut everything off, and so it's not getting everywhere.
Yeah, we also have actually already purchased some of the items, and we purchased an emergency stop button that will be on the frame, just in case there's anything wrong, you can just stop it.
Well safe.
Yeah.
Yeah, you did a real nice job, I have to say, from reading the original statement of work to what you've presented here. It really, I have a lot of optimism that it would be very successful. It looks very doable. It doesn't look like you're overburdening yourself with a lot of the programming, a lot of cost parts, which makes the assembly really easy. So I don't see any major issues with a lot of it. And like I said, a lot of this stuff you can be doing kind of in parallel. I mean, I think you could actually get quite good at image J if you committed 1 or 2 people over the winter break. So when January comes, you're like, we got this part solved. You basically gave me a
Yeah,
picture.
because we don't need
It's
anything.
like I can analyze it in a couple of minutes.
Right.
And maybe with any luck, you actually could do the whole thing in 5 minutes.
Right.
Yeah.
I can't believe there isn't some sort of post-processing in industry. It's
I
something
mean,
ubiquitous.
No,
there's probably
they give you the freedom to measure the data, but automating it so you feed it in images is something different, which I don't think you have to worry about. But I think you guys can mock something up where you get really comfortable with like rapidly assessing that. What do you envision the final demonstration? Is it going to be like kind of a secret where you don't know how big or how, you know?
Like the,
Are you talking about our spray area?
No, I mean like presumably we're gonna wheel in a panel with a nice velvet tarp on it. And we're gonna
yeah.
unrail it.
Yeah, well,
we're gonna
invite
see what
everyone
we
from
see you can
Detroit.
really do,
Yeah,
right?
yeah.
Yeah.
Well, we anticipate probably not having a blank canvas initially, and then we're going to put random spots of wherever the chemical containers, probably the surrogate we're going to be working with, the harmless, and then we'll show that we just put these random locations on and have it provide those locations.
Are you concerned at all about the smoothness of the surface? It struck me that what you talked about here was a flat surface.
Yep.
yes.
What about door handles and
Yeah, I mean,
hinges and
geometry
bumpers
is
and-
definitely something we like. At first, we were very concerned about like stuff like a tire well. That sort of geometry is super complicated, and honestly, it just poses a really complicated problem if you're going to have some sort of autonomous system to actually Spray.
Their requirement was to mimic something not unlike the side of a truck.
Yeah.
Or a truck. So nominally flat, not a lot of changes in curvature, because they don't have a Z.
Yeah.
And
programming that.
If they're thinking over imaging,
The simple plane.
they're
Adding-
imaging it in a credos
I know, but one more time, the requirement was a nominally flat surface to demonstrate that it worked.
These are supposed to be smart people.
Adding
Very
green
smart
area.
Use
people.
of complex geometry would incorporate a lot of ultrasonic distance sensors and stuff like that, just to
Oh, wait a
measure.
minute, are you concerned that the gantry has to be only a certain distance?
We do want it to keep 50 centimeters away from.
How 50 centimeters plus or minus what?
It's
doesn't move.
the further it is away, it would be less spray coverage.
Right, the closer it is.
The closer it is, it would affect our camera view angle, and then the grid size would be
So
very
about 50 centimeters.
Correct.
All right.
Well, that's another question. Distortion on your view. Okay, so you've got a camera. You're going to go. I'm going to take this picture. Take this picture. Take this picture. So what's in the center versus what's over to the side? You've got to figure that out. That's those relative kind of
Like
differences.
where the picture ends and the next one begins, or?
Because then you have to go back and map it. It's not that you're just going to go here and match up one image.
Yeah.
You've got to then send your nozzle to that
location, yeah.
to that location. So it's probably not going to be linear. The image is going to come in, and the distance out here is going to vary from the distance in the center, because you've got to send it to a precise location once you spray.
Right.
Right?
Right.
So you're going to have to account for that too, because you don't have that margin. When it's up in the corner here, what happened, the snapshot that you took, and there's one up here and one here, the coordinates here are not, the grid size changes. So, the
Right.
number of steps over to here is not going to be just twice as far.
But you just want to know that in the corner, I got problems.
I know, but
Yeah,
then I
in
want to
that
go there
picture.
too, because I got to decontaminate it.
I understand, but
Right.
once I go there, if I've got a problem that's the size of that cup, and I take my decontaminant, the size of that plate, I got you covered.
Yeah, right.
It's not
There's
like
no
we
point
did
in-
that corrosion, I gotta know.
Right. You're going to overspray on the decon is not so much the issue. I know,
Yeah. So
talked about
we-
saving materials, but you're
Reducing
going to err on the side of extra on the decon side.
We figure the way, so military, if they have any sort of contaminations, they know that location. Most likely what they're gonna do is they're gonna completely clean the whole car. So it's not, this spray is probably not powerful enough to essentially either power wash a
Yeah,
location.
yes and no. In reality, we always tend to overdo it.
Yeah.
But part of the driver behind this was not to overdo it, to be able to
Okay.
go and pinpoint things to save on materials, because when you do that overspray, that waste effluent is contaminated, and you got to do something with that too. So, at some point, when this becomes an accepted process, then the idea is going to be to start minimizing materials.
Yeah.
And so that does have to be a good,
Of course. Yeah, we remember the initial meeting we had with you.
yeah.
We were talking about the burden of removing toxic waste, and how it's beneficial to just spray the parts that are contaminated and
Yeah.
grow from that, just wash the whole entire vehicle.
Right.
Yeah.
That's the dream, is to
Yeah,
go
of
back and
course.
minimize,
Right.
But we do want to make sure that we get the initial number one priority first.
Yes.
Essentially, we're just working on a flat plane, not complex geometry. Just working on this first, and then decontaminate, then maybe even move on complex geometry.
So, once you think through a little bit, next week, maybe a couple of you want to talk to Dr. Noots and me about data processing if you need.
Of course,
Yeah,
the
okay,
resource
very
that you
helpful.
mentioned would be very
I
helpful.
was also by another department,
Yeah.
said, we have to look at,
And,
pick the
yeah.
right projects if you want.
We do
Yeah.
have to talk a little bit to the CS department as well, just to.
Yeah, given that being the most difficult aspect, and we are mechanical engineers, so we're more inclined to assembling and constructing.
But again, it's not beyond our reach, so.
Yeah, of course.
we will do
Very
our
good,
best.
good morning.
Very good, very
Thank
good.
you.
Thank you, everyone.
Thank you so much.
Bet.
See ya.
Thank you.
For attending, thank you.
Well done. Nice job. This is supposed to be rigorous, or supposed to be, I don't say confrontational, let's call it
Thank you so much.
Okay.
It's been a thorough run through what we got with that.
I think I would have done if I had